Okay, let's get started. So, are there any questions from last lecture? You see what's on the screen, right? Any questions about that? Yeah.
Is the clean star?
Cleaning star. Mm-hmm.
Is that a set of all binary strings?
It's the star operation is defined over a language. So if we had the set 0, 1 star, that would be the set of all binary strings. Or if I had 0, 1, 2, that would be the set of all ternary strings, strings in base 3. So it's not necessarily just over the language with only single length strings in it. It can be over any language that you like. So if I had like 0, 1 and 0, 1 as the language, I can define the star for that. It's just over any language. Yeah. Oh, what's that? Like, so what do you think? Can you move the tape head all the way to the left side? What would happen if I kept trying to go left? It would hit the end, and then what would happen? The machine would stop. So what do we do? So what do you do when you have the input? You shift it over one position. So let's. No, I can't add a new page. All right, I'll just do it this way. So if we had like this on the tape, 001 for example, we'll make a special character to represent the left-hand end of the tape. So what we want to have happen after this is, let's say $ is our special symbol with 0, 0, 1, and then the blanks after. So how would I go from the top to the bottom for that? Well, let's see. Where does the tape head start? For either when the machine starts up. At the very left-hand end, right? So it sees a 0. What is it eventually going to write in there? $. It'll remember a 0 in the state. So we'll have a, let's say, Q0 state right here. And then we'll say, oh, there's a 0. I'm actually going to call this QS for a reason you'll see in a second. I'm going to write a $, and I'm going to want to look at this position now. So I got to move right. So now I remembered a 0. 0 was the last character I just saw. So I'm going to call the next state Q0. It's not the start state. Okay, so now what am I looking at in the tape? The second 0. But what did I just remember? A 0. So what am I going to write to the tape? 0. So which state am I going to go to? Back to Q0, because the 0 here is going to represent what I just saw on the tape. So here, if I see a 0, I'm going to write a 0 and move right. Okay? Well, if we do that for one more iteration, we're going to land on this 1 right here. So what character did we just remember? 0, the second 0. But we're seeing a 1, right? So can I go back to Q0 on this? No, because I want to go to some other state where I just saw a 1. So I just saw a 1, but I have to write a 0, because that's the thing right before the 1 I just saw. And then I go to Q1. Okay, well, what if I was in Q1, so the 1 I just saw before, and I now see a 0? What state should I go to? Q0, right? Because the 0 for Q0 and the 1 for Q1 represent the character I just saw. So I'm remembering, in a sense, the character in the state. So if I am in Q0, I just saw a 0. If I'm in Q1, I just saw a 1. Okay, well, let's see. The transition then would be, well, I just saw a 0, but I need to write a 1 down because I just remembered a 1 right before I just saw the 0. So let's see. If we're here, and I'm looking at this 0 right here, what this diagram tells me to do is, I see a 0, I'm going to write a $sign down and move right. So I'm not going to do any intuition here. I'm just going to follow the diagram. But now I'm at Q0. It says, if you saw a 0, write a 0 and move right. And so that's what we're going to do. We're going to write a 0 so it didn't actually change, and move right. But now I just remembered a 0, but I see a 1. So what is going to appear in this cell right here, this third cell? 0. Because it says, you just saw a 1 there, but you're going to write a 0 there and move right. Okay, now I'm looking at, I'm looking here, and I see a blank. Did we handle the blanks yet? No, so we need a blank. And from here, what should I write? A 1, right? Because that's the character I just saw. And here, I think the best decision is to go left. Because should I keep moving right once I hit the blanks? No, because I'm not going to ever change. So I'm going to move left, and then after that, we can just zoom past all the way to the beginning where we wrote the $sign down. So now we just shifted the input 1 position. But of course, there are other transitions we haven't done here. And if the alphabet's larger, we need to handle that too. But this should give you an idea of remembering the character that you just saw in the state. Any questions about that? Okay, any other questions about pset 1? Yeah.
When you say construct try machine, how do you mean?
So I actually put this on the announcements page. Anyone seen the announcements page? What does it actually say? It says, if it doesn't say explicitly, create a state diagram, low-level description, or high-level description, you can do any of those 3. State diagram, low-level, or high-level, the choice is yours. Note, it's not worth many points, so it's not meant to be a hard question. Okay? But obviously for question 3 is obviously a state diagram. Other questions? Who's having trouble on pset 1 or is having a hard time? So if you can convince me that you've been working hard and you think everyone else is too, I can extend the deadline. So who can convince me? All the Piazza questions, I agree with that. Any others? If you promise to continue using Piazza and posting questions that you're confused about, do you want the deadline extended? Yes. All right. So the deadline's going to be extended to 7:06, so Friday instead of Wednesday. And I'll make the change and I'll make an announcement and all that good stuff. So, any questions about pset 1 otherwise? Yeah.
What is the fourth do question asking?
So this one, yeah.
Yeah.
Mm-hmm. So So the question essentially says, I'm going to give you an integer x in binary, and I want you to tell me that it's a super duper number, whether it is or it isn't. Okay? So that's essentially what the question asks. And what I require is that the machine that you write always stops. Okay? So let's see. If I'm given x, and let's say that I test, so this will actually be a way to help you. If y right here is larger than x, can it be a super duper power? Super duper number? No. So that should actually help you quite a bit. So now I've limited what y could be. Could you limit what alpha could be? Yeah. So what if y to the alpha is larger than x? Could it be a super duper number? No. So therefore, you've limited what alpha could be. So that should get you started. Other questions about p-set 1? Third. Okay. So what about it?
I don't really know how to go about it.
How can you calculate the Fibonacci the nth Fibonacci number? Yeah. So f of n is equal to f of n minus 1 plus f of n minus 2, and then the initial conditions, obviously. So if I want to know f of n, what things do I need to know? Right. I need to know this guy and this guy, right? Can I add two numbers in binary? Yeah, so using a Turing machine, though. So this is actually related to question 3, which is why I put that do question there, because it helps you with the other questions. So if I want to add two numbers, x and y, isn't that just repeated increment of x, y times? So let's see. If I want to figure out what x plus y is in binary, let's say, isn't that the same thing as x plus 1 plus y minus 1? Isn't that the exact same thing? What if I do this over and over and over until y is 0? If y is 0, what is the other number? X plus y. So now the essential question is, can I increment or decrement a number in binary? So this should give you an idea right here. Let's say I have this number in binary. How do I decrement it? Well, that's the answer. But like procedurally, how would I decrement this number? The first one? The least significant bit, which is in this case, the right 0. Okay, I'm there. What do I do? Change it to a 1. Now what? Go left. I look at that 0. What do I do? Change it to a 1. Go left again. Oh, it's a 1 this time. What do I do? Change it to a 0. Now what? I'm done. So now I just decremented a number in binary. How do I add one in binary? Let's change the number up. How do I add one in binary? Look, start at the right again. If it's a 1, change it to a 0. If it's a 1, change it to a 0. If it's a 0, change it to a 1. Do I keep going? No. And now we just added 1 in binary. So this is, we're going to come back to this exact thing, but the whole reason I put these questions in there is so that you can think, well, I add and multiply these numbers all the time. Can I actually do them on a Turing machine? And you have to think at a fundamental level, can I actually do these really simple operations on a computer with a Turing machine? And it turns out, yeah, you can. So the details, of course, are where you have to think a little bit. But the essential idea is, how do you add 1 or subtract 1 to a number in binary? Okay, does that make sense? Other questions on p-set 1? Yeah?
What if the number is like 11111 and we have to
Add
it?
So if we're trying to add 1 to a to a number that's all 1s, so how do I add 1 to a number that's all 1s?
Make them all zeros and add 1.
Yeah, make them all 0s and put an extra 1 at the beginning. oh, but wait, if I'm confined to a certain space and I need one more position, what do I do? Shift everything else right.
So then use
You see how like everything works together to solve these problems? Yeah. So yeah, if you detect it's all ones, then shift everything else right, which is not hard to do. But here's a thing you might want to think about. So suppose that we did have that situation where we had a giant number of ones in a row, and we had some other stuff over here, and then we're going to add one to the number, so then we have 1, 0, 0, 0, and then we shifted everything else right to there. How do I come back to that exact place? Because if I have a whole bunch of these number sign separated things throughout the tape, how do I come to that exact set of pound signs again? I don't have a way of marking that it's there. I suppose what you could do is put an X right there. And then you can say, oh yeah, that's where I was. But a more common way to do it is to have, in addition to every symbol on the tape, we have another symbol that's what is called a dotted version of that symbol. And we'll come back to this a little later today. And so I call this a 1 dot, but you can also have a 0 dot, a pound dot. And what this dot is supposed to represent is another character to represent where the tape head was before you had to do other work, like shifting stuff. So if you have like a dotted version of that symbol and you put that dot there, then you can come back to there and then undot it or whatever. Okay, we'll come back to this idea. Other questions about P set 1? No other questions about P set 1? Yeah.
So for a few of them, you asked for us to justify why it decides.
Like which one?
For I think number 3.
3?
Justify why your TM is a decider.
Mm-hmm.
Do you want us to do that via definition, via proof, or via examples of?
Well, it says briefly. It says briefly. Yeah. So you can just say, well, for example, the numbers here are finite, and so I do a finite number of operations on a finite length string, so therefore the number of operations is finite. So like that'll be like 1 point out of the 6, so it's not worth much. It's just so that you can actually do a justification for why it actually halts in a finite amount of time. We'll actually show eventually that you can't prove that an arbitrary Turing machine halts. So it's not like you can give me yours and then I can say, yeah, it actually does halt or it doesn't halt. So that's why we have a justification here. Other questions? Yeah.
Do problem with CSE355.
Can I do that one?
Not do it, just the first part A, I guess, is.
Yeah. So we actually just did part A. Where we have an integer x written in binary, and I subtract 1 from it, and then I stop.
Yeah.
Didn't we just do that?
I'm kind of confused about the problem is we're not given M, but we can.
So all this is just it's going to help you with determining the runtime. That's all it is. You're not given M, you're just given an arbitrary number. And all that is for is, well, if I have T transitions left, execute 1 transition, decrement T by 1,
Yeah.
and then go back. That's the entire purpose, just to show you how long the runtime takes.
Oh, okay.
Yeah. Other questions about P set 1? Okay, let's get into actual material. Okay, so what were the last few things we talked about last time? We define 2 types of languages. One, languages can be Turing recognizable, and can anyone tell me as a refresher what does recognizable mean?
some TM recognizes.
Right, the Turing machine recognizes it, but what does that actually mean? It means that for the strings in the language, the Turing machine accepts them. Right? That's all that means. What about the strings not in the language? Does it have to accept those? Oh, I mean, sorry. Does it have to stop on those? No, it never said anything about those. It said it had an accepting computation on the strings in the language. It didn't say it had a rejecting computation on the strings not in the language. It never said that. Just only on the ones in the language. What about that other one? It's a recognizable, or it's Turing decidable. And what does decidable mean? Yeah, so it always halts on every single input that it could be given. So it cannot possibly ever run forever. Okay, that's all that it means. It means that a formal way to say it is, it always has an accepting computation on the strings in the language, and it always has a rejecting computation on the strings not in the language. Remember, computations are finite in length. Okay? Any questions on that? So tell me whether or not this is decidable. So is sigma star decidable? The set of all strings. Yeah, why is it? Yeah, if I'm given an input, is it in sigma star? Yeah, because any string's in sigma star. So I don't even need to look at the string. I just go to QAccept immediately. And so therefore, I will accept everything. What about, say, the empty set? The set of no strings. Is that decidable? Yeah, why? Yeah, just go to QReject immediately, right? So you don't even need to look at the input. So there are going to be quite a few decidable languages that you can think of. Like, for example, how about this one? The set of all binary strings where W contains a 0. There's a 0 somewhere in the input that you're given. Is that decidable? Yeah, so it's not as trivial as the first two, but how would you decide it? Yeah, just move right. If you ever see a 0, go to which state? QAccept. And if I never see one, and how would you determine that you've never seen a 0? Hit a blank, and then what do? Go to QReject. So, of course, we can talk for the rest of the semester about examples about decidable languages, but what we want to do is be able to characterize what languages are decidable and which ones are not. So a really short, our very first theorem, but it's actually quite easy, is all decidable languages are recognizable. So let's just say that that's true and we've proved it. What can we say about these first three languages then? We just showed that they're decidable, so what else do we know? They must be recognizable. So why is this true? The theorem statement true? I have in the notes, follows from the definition. But does it really? What does decidable mean? It halts on all of the strings in the language, and it halts on all the strings not in the language, right? What does recognizable mean? Halts on all the strings in the language. Does it have to run forever on all the strings not in the language? Does it have to? Is anything in the recognizable definition say that? No. So doesn't that show that all decidable languages are recognizable? It just satisfies an additional criterion that is not required by recognizable. So in fact, so the really short proof of this is any decider for a decidable language halts on all strings, and any recognizer for a recognizable language halts guaranteed. It might do this on the other strings too, on strings in the language. And so therefore, the decider must also be a recognizer. Okay? Any questions about that? This might be one of the easier theorems that we'll prove, but it's just that 99% of the time in this class, if you're unsure of something, re-look at the definition, because the definition is precisely defined and it should really help you with if you're not quite sure why something's true. So all we did here was appeal to the definition of those two things. Okay, so of course we did an example of a state diagram for a Turing machine, but as you can see, that's quite cumbersome in general because you need to be able to handle a whole lot of subproblems at once, and that's not really very fun. So what we do from here on out, until we get to other things, but for Turing machines, we talk about what are called low-level and what are called high-level descriptions. So this kind of spelled out in the piece, in the problem set, but I got several questions about this, and I think it bears repeating. So a low-level description, so these are not going to be precisely defined, and the line between the two is a little blurred. So, and opinions may matter here, but the general idea behind a low-level description is if a moderately good person in this class looks at this low-level description, they can turn that into a state diagram. So they look at the low-level description written in English, or whatever language you like, and they can convert it to a state diagram. So anyone moderately experienced can convert it to a state diagram. So the things that you need to say here in general, what you need to say what the tape head is doing. Like, is it moving right? Is it moving left? That sort of thing. What is written? And things along that nature. So you're giving a low-level understanding of what the machine is doing, but written in English, instead of this absolutely formal schematic, this state diagram. So what do you think a high-level description would be then? It's actually the exact same thing, but you can convert the high-level description into a low-level one. So it's an abstraction from the low-level thing. So it's exactly the same thing, but to a low-level description. And for these things, like what the tape head is doing, what is written, those are not actually important. What is important is the higher level thinking of what the machine's actually doing. So another way you can think of this is pseudocode. And oftentimes that's exactly what it is. So you don't need to do anything low level at all here. You just give the higher level thinking here. Any questions about those two? Okay. So let's talk about an example of a low-level description. So I'm going to skip example 3 because it's quite short, and we'll come back to that for a high-level description. But we'll do a low-level description for example 4 first. So it's defined as L3 in the PDF. So here, what you have are a whole bunch of strings that are delimited by this pound sign. And each of these is a binary string. So and none of them have the pound sign inside them. And all of the strings, I'll just say it informally, all of these strings are different. I wrote it formally in the PDF, but this is essentially what it is. If you have two different indices, they must be different strings. So if I look at W1 and WK, those can't be the same. If I look at W4 and W6, those are different strings too. Every pair of strings is different. Okay? So what's a high-level algorithm to, if I'm given this on the tape, if I'm given W1, W2, all the way up to WK, let's say, what's a high-level way of trying to figure out whether this string belongs in L3 or not? What's a high-level way of doing this? So I don't want to know what happens on the tape. I don't care. I just want the general high-level idea.
Compare every pair of strings. Right,
compare every pair of strings. So what's the way I can compare every pair of strings? I'm not worried about the comparing yet. We'll worry about the comparing later. How do I get to every possible pair of strings here? Well, I have where the separations are, so that's not an issue. Well, let's just say I'm looking at that one and I'm looking at that one right now. Okay? What is a way that I can figure out what's the next pair I can look at to compare? Yeah, like a for loop. So what would be a way to do this as a for loop? So for, let's just say that this guy's the I index and this one's the J index. So where does I go from and to? What does it start at? It starts at 1 and it goes to, be careful, K minus 1, right? Does it go to K? No, I don't need to check that. Because if I check I and J this way, isn't that the exact same thing as if I switch them? Right, so I only need to go to K minus 1 here. So where does J go from and to? For J equals, where does it start? Not just at 2, but it goes from I plus 1, right? If I was, so it's not literally me, but if I was right here, where would J be? Would it start at 2? No, it would start at wherever I is and then 1 position over. And then 2, where does it go to? To K, because it can go all the way to the end. And then, so we just compare Wi and Wj. Reject if same. And then if we've looked at every single pair, what should we say? And we found that they're different. We should say except at the very end, once we're done every iteration of the loops. Okay? Does that make sense? So now let's go down to a low-level description. So let's, I'm going to just erase this part right here and leave the high-level idea there. How do I actually mark? This is where the I position, the ith string I'm looking at is, and the jth one is. How do I actually mark that there? I can't like put an X somewhere like in the beginning of the string like I just said. I need to remember what character was there. Because if I just put an X there, I don't know what character was there. And when I check the ith string with the j string, they might be the same, they might be different, right? So what is a better way to do this? So let's actually do an example because it can be quite useful. Like that. So how would I actually mark I'm at the ith string right now and where the j string is. And I kind of alluded to it earlier. Yeah, I have a dot symbol. So this is just like an X symbol, but this tells me, hey, a 1 was there, even though this is a completely different symbol. A 1 was there, and so now I can actually use that to compare against another string. So what we could do is avoid the dots on the 1s and 0s, and then just dot the pound signs. Okay? If you just dot the pound signs, then I don't need to handle that 1 and 0 dotting business. And so now I look and say, hey, the first dot that I see is right there. And then I look, okay, here is the second dot, wherever it is. And then now do I know where the strings are? Yeah, they're just to the right of where the dots are. So here's the first dot. Where's the string associated with it? Just to the right of it. What about this one? Just to the right of it. Okay, so are these two strings the same or different? Different. They have different lengths, so they must be different. Okay, now I need to check another pair. What do I do? Wait, jump which dot to where? Oh yeah, the right dot, because I'm not quite at the end for the first dot. So I move this dot over to here. Okay? And I undot this one because I should only have 2 dots on the tape. Okay? Just to clarify, dotting is not a process of a Turing machine. It's a completely new symbol, but it just helps us to know where to check the strings. Okay? So now which strings am I checking against? First and the third one. So we check this against this, and we see definitely they're different. So then now what do I do? So I need to move this guy over to here because it's not the last pound symbol. But we see that there's nothing after it. So what should I do now? Move this guy over 1, right? So that's easy. Now what? Move the right one back to here and 1 over. Because I may have many it needs to go backward to, but I need to move 1 over. And then now I check, oops, I erased the wrong one. So now which strings am I checking? This one and this one. And we see they're different. So now what do? I move this guy over to there. And we see, oh yeah, there's no string over there. So then now what do? Move this guy over, oops, to there. And then now I check what strings? Oh, well, first I have to move this guy over, but we see it'll actually end up at the same place. So now what strings am I going to check? Yeah, well, 1, 1, but there's no string over here. So we have to move this guy over 1 place. Right? But then we see, oh, we're all the way at the end. Are we done? Yeah, there's no other strings to check. No other pairs of strings to check. So what should I say on this input? Except. And if they were if any pair was the same, then we would just go to Q reject immediately. So that's what the English description in the notes has. I'm giving you a picture-based representation of that, but that's all we're really doing. We're keeping track of which 2 strings to compare. But now here comes the hard part. How do I compare those two, let's say those first two strings to see if they're the same? So now we get back to the dotting business. right? So what we do is we start here, and we say, oh, that's a 1, but I want to mark that I just saw a 1. So I'm going to put a 1 dot instead of a 1 there. Then I go where? I check which character over here. In the place right after where the dot on the pound sign was. So I keep scanning right until I say, oh, here's the dotted pound sign. Now the string is to the right of me. But what am I going to look at next? The first undotted character on this side, which is that one. So is that the same as the one we saw earlier? Yeah, so I dot this guy. Then I zoom past going left, look for the first undotted character on the left side, which is a 0. So I dot this one, and I remember a 0 in the state, as we said earlier. Then I zoom right, look for the first undotted symbol on the right after that pound sign. Then what? Is it a 0? Is it a 0 here? Yes. And so I dot it, so that's good. Then I zoom back. I look at the first undotted symbol here, which is a 0. Then I zoom going right, looking for the first undotted symbol, which is a, is that the 1? Is that the same as a 0? I hope not. And so are these two strings the same? No. What if instead I had a 0 here? And then I dot this one, I come back, I dot the 1 over here. I run into a pound sign. Are these strings the same? No, why not? Because they're not the same length. So, okay, so let's just say that they're not the same string. I'm over here. Now what do? I move back left. What do I undot? Everything except the pound signs. I got to keep those there because I need to know where the next pound sign needs to be. But I undot everything else. And so I go from here, I zoom all the way back. Now I need to move the second pound sign, and then we continue from there. Does that make sense? So that's what the English description is in here. If there are no questions, we can do the example 3, but at a high level. So this is a low-level description. So this is L1. So this is powers of 2 number of zeros. So note, the n up here actually is 2 to the power n, but the 0 down here means 0 repeated 2 to the n times. Okay? So, and this will come up again and again, where you have a power upstairs, but it's just concatenation at the bottom. So like, for example, 0's in there. Yeah, 0's in there because 2 to the 0 is 1. 2 to the 1 is 2. So 2 zeros are in there. Is 3 zeros in there? No, 4 is in there, and then 8, and then 16, and so on. So if I give you a whole bunch of zeros on the input, how do you tell it's a power of 2 or not? What if you divide by 2? If you divide by 2, like cut the list in half, what should it be? Should it be a power of 2 again?
Yes.
Yeah. Keep doing this until when? Until you have exactly one of them, which is also a power of 2. But if you go down all the way down to 1, then was the original input a power of 2? Yeah. So repeatedly divide input in 2. If not possible, divide input into until exactly 1, 0 remains. If not possible, which means we can't divide by 2 at a particular point, what should we do? Reject, because it's not a power 2 at that point. But at this point, it must be a power 2, so we accept. So I hope what you can gather from these two examples is that there is quite a big difference between a low-level description and a high-level description. But of course, one person may think, I'm an assembly programmer, and I think this thing is incredibly high-level for me. So it's entirely up to your opinion to some extent, but you're never wrong by providing more detail. If, for example, on a test, although I wouldn't ask this on a test, if I gave you that and I asked you for a high-level description, it wouldn't be right to say, check if the input is a power 2 in length or not. So yeah, that'd be a little too high level. I need some idea there. But I hope you can see that there is a difference between these. Are there any questions about the difference between the two?
Was the last example a low-level description with the dots?
Yeah, with the dots, that's a low level. And this one from before for the checking if they're different, that would be a high level one. Yeah. Yeah, so there should be quite a big difference between the two. And precise and formality here is not really that necessary. It's conveying the idea that's much more important. So like on a test or on a problem set or something, you'll get many, many more points for giving the idea than all the precise details. You might not get a perfect answer, but you'll get a majority of the points, let's say, for even just describing the details. You can even go and say, I don't know how to proceed, but I have this idea and I think it works, but I don't see how to proceed further. That would get you quite a few points out of that. So it's the ideas that are important, not the details. Unless it's like an extremely easy question, then of course the details are important, but yeah. And are there any questions before we do some more fun stuff?
So, dotting is usually does not take place on the Turing machine. The Turing machine usually ships it.
I'm not sure what the question is.
So it's saying we dot everything, right? So like one dot.
Mm-hmm. Yeah. Mm-hmm.
So does it actually happen on Turing machine, then, or there are any different characters or symbols?
Yeah. So like, for example, if the input alphabet of this guy is obviously 0, 1, and pound, then the tape alphabet is going to have, it must have those same 3 ones and the blank symbol, of course, but it also will have 0 dot, 1 dot, pound sign dot. Yeah. So if you wanted to write that down formally, then you can do it that way. But like in a low-level description, you don't have to say this is the tape alphabet or whatever. Any other questions? Yeah.
For the low-level description, do you just like show the use like by steps, or do you want to describe the steps?
You should write it as like an English description. I'm doing this to save time, but something like what's in the notes would be desired. But giving an example is never wrong, but it can't like give you all the points, let's say. Yeah.
When you were comparing strings, you had the dots, and you said you would keep on moving back until you hit a character with a dot. So you wouldn't have to actually remember or know which character, and you're just looking for any character that has a dot on it.
So like, you mean when we're comparing two strings?
Yes.
So if we're like comparing this one right here and this one, and let's say we're like in the middle of this,
right.
And then now we're gonna dot this guy, the second 0 on the left side.
Right. You were saying you just keep on moving back until you hit a character with a dot.
But not quite. So we dot 1 on this side. We keep moving back, seeing whatever, until we hit a pound sign dot. then we must not be able to see any dots until we saw the last one that was dotted. So it's like the zeros again, $ zeros again we covered last time. So we put X's until we zoom back and see, oh, we finally hit an X. The one to the right of me must be the first thing I haven't looked at yet. So it's the exact same thing here. You could just say, instead of this whole dotting business, I'm going to have the 0 dot represent X, 1 dot represent Y, and # dot represent Z. It doesn't actually have to be dot, but it's just easier to visualize that way. Any other questions about these? Okay, so let's go on to, so the nice thing from here on is that until we get to other material, like in 2 weeks or something, is that we're going to ignore the low-level descriptions now and just stick to entirely high-level descriptions, because the things we're going to talk about are much more important in concepts versus all of the details. But of course, since it's a high-level description, you should at least be able to think, how would you be able to convert it to a low-level description? So we've been talking about these decidable languages and recognizable languages, and we may want to think, well, what are other decidable languages? Like, if I have a whole bunch of decidable languages right here, are these the only ones, or are there others? And let me ask you, what is a language in general? It's a set of strings. Well, when you see set, what do you want to do with sets? How about union, intersection? And what are some of the other operations we defined? We defined star and more simply than star. How about concatenation of the two languages? We talked about that last time. And so maybe we can say, oh, if I have two decidable languages, is their union decidable, or their intersection, or something like that? And so if we have so let's let C be not a class, collection of languages, and we say C is closed under operation, this symbol is called an O+, but we're going to give specific operations. I'm just defining it in a general context. We say that it is closed under operation O+, if for any two languages that you pick out of C, then if you apply this operation to L1 and L2, then the resulting thing is also in C. Then L1, O+, L2 is also in C. So if we can show that decidable languages are closed under union, let's say, then if you pick any two decidable languages you like, form their union, that's also decidable. For intersection, form their intersection, then that must also be decidable. So what we will show is precisely that. So decidable langs are closed under union, intersection, concatenation, and star. Actually, and complement in this case. Okay, so all this means is that if you take any two decidable languages, ignore complement and star for a second. If you take any two decidable languages, their union is decidable, intersection is decidable, and concatenation is decidable. If you pick any decidable single language, a single one, form the star of that language, that's decidable too. and the complement of that language is also decidable. So that's what the theorem says. So this one's a little bit more substantial than the previous theorem, actually quite a bit. So how would I show that decidable languages are closed under union, for example? So if I have two decidable languages, let's let L1 and L2 be decidable. Right off the bat, what does that tell you? Just from the definition of decidable. There is a Turing machine that always halts for those two languages, right? That's entirely what the definition says. So whenever that sort of thing happens, make a name for it, for those Turing machines. So let D1 for decidable, not Dougherty, be deciders for L1, L2. So let's see. I want to make a decider for L1 union L2. So I'm giving you an arbitrary string, and I want you to tell me whether it's in L1 union L2 or not. Okay? How do you think we can do that?
Go through one machine first, and if it's rejected, then put the head back, and then just go to the start state of the second.
Mm-hmm. We actually don't even need to be that low level. So we're going to only stick to high level here, but you're right. If it was low level, that would be what you do. So that's the idea. We run it through D1. If D1 says accept on that input, what should we say for the union? Is it in the union? If D1 says yes, it's in my language, is it in the union? Yeah, because if it's in one, it's in the union. If it says no, it's not in my language, what do? Should we say reject? No, what should we do? Yeah, check it for the under D2. If it says yes, what do? Accept. It's in the union. If it says reject now, no, both of them said no. So could it be in the union? No. So in fact, we can. So now we need to justify that it actually runs in a finite amount of time. Does it? Yeah. Why? Right, the two machines are guaranteed to halt because they're deciders. So running one, then running the other, whatever that amount of time takes, it's still a finite amount of time. So it must be a decider, whatever machine we are, what we just talked about. So the way that we write these high-level things is we say on input, let's just call the input string W, whatever it is. So this on input means the machine that we are making has W written on the tape. But we're not going to think of the tape here. So to check whether D1 accepts the input, we say run D1 on W. If D1 accepts W, what should the machine that we're making say? If D1 actually does say yes on W, it should also say accept. So we say accept. Otherwise, which means it rejects W, we continue. What should the second step do? Run D2 on W. If D2 accepts W, what should we do? If D2 says yes, then we say accept. Otherwise, which means, did both machines just say reject? Yeah, oh, so what should our machine say? We should also say reject. And we know it runs in a finite amount of time because both machines run in a finite amount of time. Any questions about that before we de-stress? All right, let's take a 5-minute break.